we're going to go ahead and get started on a lecture here talking about the four major biochemicals, which as you can see are carbohydrates, lipids, nucleic acids, and proteins. We're going to talk about carbs and lipids and a little bit about proteins in this lecture. And in the next lecture, we'll finish up on proteins and nucleic acids. So let's start right out with carbohydrates. They are composed of carbon, hydrogen, and oxygen. This is typically in a 1 to 2 to 1 ratio, which means, see if I can write this here, right on the bread, 1 to 2 to 1 ratio. That means for every carbon, there's going to be 2 hydrogen and 1 oxygen. So if I have 6 carbon, I'm going to have 6 times 2 hydrogen, or 12, and 6 times 1 oxygen, or 6. That's, if you remember this, we talked about this once before, C6H12O6. It's a 1 to 2 to 1 ratio. That's glucose that we talked about in class. In fact, we did the demo with the sulfuric acid and the table sugar, and we were talking about that as being C6H12O6, the sugar. So let's get into some examples here. When you think of carbohydrates, here's what I mostly want you to think of: sugars and starches. Right? However, the more complex carbohydrates help form very important things in life. For example, in plants, it helps to form something called cellulose. Let's see if I can write that up here real quick so you see how it's spelled. Cellulose. That's kind of like the strength inside the plant cell. And cellulose, being such a strong product, helps trees grow very tall. They can support themselves. It's also known to us as fiber. You can't digest it, so it sort of plows through your body and keeps your digestive system cleaned out. And you look over here, the exoskeleton of insects is made of a carbohydrate called chitin. So when you step on an ant, that little crunching sound you hear, that's that chitinous exoskeleton composed of carbohydrates. When we talk about carbohydrates, we can categorize carbohydrates into categories based upon how large they are. Just one little unit of carbohydrate we refer to as monosaccharide, which should make sense because mono means one. Some examples of that are glucose, fructose, which is sugar that comes from fruit, sucrose is an example of, actually not of a monosaccharide, but of the next one, a disaccharide. Di means you have 2 carbohydrate units that are bonded together. So with sucrose, what we have is a single unit of glucose that's bonded to a single unit of fructose, and that forms sucrose. That's your table sugar. So me giving that formula C6H12O6 in the little demo I did the other day was a little misleading. Table sugar is actually a little bit more complex. Lactose that you find in milk is a disaccharide. It's a glucose molecule and a galactose molecule. And that's going to be one that we spend a lot of time talking about. In fact, we're going to do a lab on that. About 2 labs from now, we're going to do a lab dealing with lactose. If you have more than 2, then you have what's called a polysaccharide. Poly means many, right? So you could have, 4, 5, 10, 20 units of carbohydrates bonded together. And examples of those are starches, cellulose, chitin. Those are ones we talked about. Glycogen is one we haven't talked too much about. That's I think I talked about it in class a little bit. That's where all your energy storage, that's what it's stored as. It's stored as glycogen. You have a big spaghetti dinner. You'll store that extra carbohydrate energy for a little while in your liver in the form of glycogen. So here's what carbohydrates do for your body. Number 1, energy supply. Carbohydrates are great energy supplies. They add structural support, cell recognition. That means there's little antenna on cells made of carbohydrates, and those antenna allow cells to communicate with each other, so they can recognize each other, make sure that they know that you belong in the body. Otherwise, the object will get attacked by your body, by your immune system. Next thing I want to talk about are lipids. Lipids are your fats, you see it all here in the steak, your oils, your waxes, and even your steroids, which are most commonly, we're talking about hormones that exist in your body naturally, and there's the unnatural steroids. I'm going to get right to the chase here. What lipids do, they are also a way of storing energy. It's a long-term storage of energy. So if you have more energy in your body than you need, let's say you eat like a spaghetti dinner every night, but you're not going to burn all those carbohydrates. So what your body will do is it'll convert those carbohydrates into fats, into lipids, which become a long-term storage for energy. Insulation. You think of like the blubber on whales. It acts as a great insulator so they can swim through very cold waters. It helps control water movement. It behaves like a reverse rain jacket on plants, so that waxy outer coating on a leaf, that's actually a lipid, it makes it so that water can't easily escape out of the plant, that's what I mean by reverse rain jacket. Instead of not letting the water in, it helps to not let the water out too quickly. And it's a shock absorber, right? Here you can see what I was talking about with the plant. When it beads up on the leaf and just rolls off, it's called a cuticle. It's a cuticle of the leaf made of waxes. It's a great picture. The carbohydrates, pound for pound for energy, to have the same amount of energy from carbohydrates, you're going to eat a lot more of them. Fats, on the other hand, to have an equal amount of energy, you don't have to eat as much, which is why fats are preferred by especially migratory animals that need to get a big, like this bird needs to get a lot of fat in its body to save up, so when it migrates, it has energy. If it tried to get the same amount of energy from carbohydrates, this bird would be so big its little wings wouldn't be able to lift its body. And it looks like it gets pretty close here. In fact, there are stories of some birds that will get so much fat loaded up before they migrate that their eyes practically swell shut. Alright, I want to show you guys a video, I think a pretty cool video showing fat storage and how it's useful. So here we go.
Paul Hopfensberger is attempting to swim 21 miles across the English Channel. Surprisingly, his training involved gaining 16 pounds of fat. His fat cells have grown, weighing Paul down in the arms, chest, and belly. It's more athletic than it sounds. This is what our early ancestors probably looked like. For them, fat was a vital way of storing energy. As he heads out into the frigid water, the key to his success will be how Paul manages his body's fuel reserves. To start with, carbohydrates from Paul's last meal, stored in the liver and muscles, are quickly converted to glucose, then combined with oxygen to power him forward. Paul's muscles are now burning 3,000 calories an hour. It's what you'd get from 3 large hamburgers. But after 3 miles, the easy access glucose is running out. He's facing a fuel crisis. It's a critical point many other athletes know as the wall. This is the moment that marathon runners dread most.
The average person has about 2 to 3 hours worth of energy. Once that is depleted, then you have what's called hitting the wall, where you just feel this physical fatigue and even this mental anguish, like you're just done, you need to stop.
The brain detects low blood sugar levels, and that makes you feel so bad you want to give up. But if you do keep going, the brain is forced to trigger a new source of fuel. To get it, the body does something truly astonishing. It begins to cannibalize itself and starts feeding off its own fat. Surprisingly, we never gain or lose fat cells. The same ones just shrink or swell according to how much fat we're carrying. When glucose runs low, we tap those fat cells as sources of reserve energy. But fat takes longer to process than carbohydrates. It's the gap in supplies that trips up the runners. Just like the runners, he must also switch fuel supplies and start consuming his own fat. Paul's extra layers have added 60,000 calories to his fuel tank. It's 10 times the energy of the glucose his liver and muscles contained when he dived in. But the process of converting his fat into fuel calls for extra oxygen, ramping up the demand on the lungs. He's now sucking in 48 gallons of air a minute, absorbed through tubes narrower than a human hair and across tiny membranes, with a total surface area equal to a baseball diamond. It gives him the strength to cover 12 miles in the first 6 hours. But that's only halfway. He'll need to keep pumping fuel to his muscles until almost nightfall to succeed. The fact is, we all have bodies engineered like Paul's. It's just that his has been tuned up through practice. The focus of that training has been to raise the performance of his heart. Paul has lost over 14 pounds of his body fat during this swim. He's used more calories than most of us use in a week. Yet we're all designed to store and expend huge amounts of energy at this rate. Despite his fatigue, he keeps his heart and muscles going for the final push. After 14 exhausting hours, Paul's foot touches sand. He's made it.
All right, now I want to talk about proteins. We're just going to start covering proteins just a little bit. And, of course, this is when you've heard a lot about, you guys pretty much know what proteins are. It's the meat, it's the milk, it's the cheese, the beans. These are all things that give you proteins, a very important part to your life. And before we really get into it, I want to talk about proteins, how they form, okay? And I'm going to use these little play toy snap beads as an example. So proteins are formed from these single units called amino acids, right? And so in the pop bead world, it'd be like a single bead. That's an amino acid. A protein is when a whole bunch of amino acids click together, right? And here's the real amino acids. Here, there's some of these. If you look at them closely, you might recognize like tryptophan. That's stuff from your Thanksgiving turkey that makes you kind of sleepy. But these are about 20 or so amino acids that are essential to life. Some of them you make in your body. A lot of them you have to get from your diet. Oops, there we go. So here's the basic chemical structure of an amino acid. You have your amino group, a hydrogen linked up here, something called a carboxyl group, and this R right here is the thing that changes. So whatever that becomes gives you your different amino acid. And we don't need to go into details on that right now, but just wanted to show you that. So when you snap those amino acids together, you have essentially made a protein. Some of them might be, 10, 20 amino acids long. Some of them might be hundreds of amino acids long, put in specific order to make a specific protein. If it's switched up, then you don't have the same protein. Now, a protein starts going through what we call protein structure, the shape of it. The shape of a protein is extremely important. It's like origami. If you fold everything correctly, you get your bird. If you make one wrong fold, your bird looks kind of funky. It doesn't work. Proteins are the same way. To get a certain protein, it has to fold and link together a certain way. If it doesn't, then you don't have that protein. And there's 4 stages. The primary stage is when you just have all the amino acids linking together like this. The secondary stage is when it begins to slowly fold a little, like you see here. The tertiary stage is when it really begins to fold in on itself. This is an actual picture of a protein. Here's my bead example. It really begins to fold up. And the quaternary stage is when you get several different proteins. Here there's 4, a green one, a blue one, a red one, an orange one, that all kind of bond together. I went through that quick. Let me show you a picture of this though. here's your primary stage, right? The primary structure. It begins to slowly fold up in the secondary structure. Then the folding becomes a little bit more intense over here in the tertiary structure. And then this doesn't happen to, not all proteins go into a quaternary structure, but some do. And that's when you have many different proteins kind of linking together. And that's where I'm going to stop. Next lecture, we're going to talk about the Pac-Man dude here and what enzymes are. But we have a little lab I want to go through where we get to practice what a protein, a carbohydrate, and lipids are. Okay, we'll see you then.